Good afternoon, everyone. So, welcome to my YouTube channel, Maths Avatarm. Okay. So, today we are going to discuss third lecture of uniform continuity. Okay. So, let's start today's lecture. So, we start today's lecture by this theorem. Okay. So, let A, B belongs to R. Okay. Such that A is strictly less than B. Okay. Okay. If A close interval, if F on closed interval AB to R is a continuous function, then F is uniformly continuous on AB. Okay. So it means you take any closed interval, closed and bounded interval. It means A and B belongs to real number. It means A and B are finite real number. Sorry, A and B are finite, okay, values. And so we are taking a function f on closed interval AB to R. Then every continuous function of closed and bounded interval AB is a uniformly continuous function. Okay. So let's provide its proof. Okay. So in last lecture we have proved a theorem, theorem in which we have stated that the two statements are equivalent. If f is uniformly continuous on AB, you take any two sequences in interval whose difference tends to 0, the image sequences difference is also tending to 0. Okay. So if possible, suppose that f is not uniformly continuous on on AB. So what does it mean? We will prove this theorem by contradiction. So we are assuming that the function is not uniformly continuous. We will prove that this produces a contradiction, then our theorem will be proved. Okay. So by last class theorem, we have studied a theorem in last class that if f is uniformly continuous, then you take two sequences in the interval whose difference is tending to 0. The image sequence also tends to 0. Now we here f is not uniformly continuous. What does it mean? It means that there exist two sequences such that xn minus yn tends to 0, but fxn minus fyn does not tends to 0. Okay. So what does it mean? What does it mean? It means there exists epsilon greater than 0 and subsequent xnk of xn and ynk of yn such that xn, such that such that fxn minus fxnk fxnk minus fynk is greater than equal to epsilon. Okay, so let's say it's 1. Okay, now since xnk and ynk both are in closed interval AB. Okay, so closed interval AB is complex set in R. So what is the speciality of complex set in R? If you take any sequence is in a complex set in R, it has always a convergent subsequence. Okay, so it means x and k 1 is subsequence of x and k such that x and k1 tends to some x naught in AB. Because if you take any sequence is in a complex set, it always have a convergent subsequence. Okay. Similarly, x similarly y and k1 is subsequence of y and k such that y and k1 tends to y naught in AB. Okay. So, okay. 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 So, sorry, 1 minute, sorry. So, we are not taking till now. So, choose y and k subsequence of y and k whose indices are same as that of x and k1. Okay. So we have sequence x and k1 which is convergent in a closed interval AB. Similarly, we are taking corresponding term of sequence y and k and we are saying it y and k1. Okay. Okay. So now y and k1 is also a sequence in AB. So it will have convergent sequence. This implies there exists y and k2 subsequence of y and k1 such that y and k2 converge to y naught in AB. Okay. Okay. So therefore what we have? So we can take x and k2. That is subsequence of x and k1. So the original sequence converges to x naught. It means this sequence will also converge to x naught. So what does it mean? We have x and k2 converging to x naught and y and k2 converging to y naught. Okay. So two things we got whose their two sequence indices are same. Okay. Indices are same. Okay. Indices are same. Okay. Now we have f, x, and k2 minus y and f, y and k2 greater than equal to epsilon. Okay. So we have one result. F is continuous at some point x naught if and only whenever you have a sequence converging to x naught, then fxn converging to fx naught. This is a criteria of continuity for a function. A function is continuous at x naught if and only whenever you have a sequence xn converging to x naught, fxn will converge to x naught. So we have two sequences. This is converging to x naught and y and k2 converging to y naught. What does it mean? It means f x naught minus f y naught is greater than equal to this. But epsilon is greater than 0. What does it mean? It means f x naught minus f y naught is still greater than 0. So what does it mean? It means f x naught is not equal to f y naught. Okay. But suppose we have a function. If x naught is y naught is equal to, then we imply that f x naught is equal to f y naught. But if f x naught is not equal to f y naught, what does it mean? It means x naught and y naught cannot be equal. Otherwise, their functional value become equal. So here, what does it mean? It means x naught is not equal to y naught. So we got this equation too. Okay. But we have this one. F, we know that the original sequence xn minus yn tends to 0. So what does it mean? X and k2, this is subsequence of xn. Y and k2, this is also subsequence of y. This is subsequence of yn. So this will also tend to 0. Okay. So, but this sequence already tending to x naught, y naught. So what does it mean? X naught minus y naught is equal to 0. Okay. Because x and k2 and y and k2 are tending to x naught and y naught respectively. So what does it mean? It means x naught and y naught, because this limit is tending to 0. So limit is x naught, y naught, so this is 0. So what does it mean? X naught and y naught is equal to 0. 2 and 3 equation are contradicting each other. Okay. Equation 2 and 3 are contradicting each other. Hence, f is uniform. Hence, fxn minus fyn tends to 0. This implies f is uniformly continuous on AB. Okay. So we have proved that every continuous function on a closed interval AB, where A and B are finite. Okay. Then every continuous function on a closed interval, closed and bounded interval, function becomes uniformly continuous. Okay. So note that we have fx is equal to x square. In last class we have proved that fx is equal to x square and fx is equal to x cube are not uniformly continuous on R. But you take any A and B. This implies but for A and B in this range, fx is equal to x square and fx is equal to x cube. Fx is equal to x cube are uniformly continuous on AB because they are continuous function on any closed interval. Because they are continuous on the whole real line. You take any closed interval, bounded interval, they are function going to be continuous. And we know that if A and B are finite numbers and you take any continuous function on this closed interval AB, function is going to be uniformly continuous. Okay. Therefore, these functions are uniformly continuous. Even they are not uniformly continuous on R, but they are uniformly continuous on AB. Because A and B are finite. Okay. So we are going to see another result. So what is meaning of extension? Let f let I1 is containing I, where I is interval and I1 is also interval, but it is contained in I. It means I1 is sub-interval of the interval I. If let f f1 I1 to R is a function. If there exists a function f I to R such that restriction of f on I1 interval is nothing but f1 function. It means fx is equal to f1x for all x belongs to I1 interval. Then f is called extension of f1 on I. Okay. Okay. Moreover, if moreover if F1 is continuous and if there exists F continuous function on I such that F definition on I1 is F. It means Fx is equal to F1x for all x belongs to I1. Then F is called continuous extension of F1 on I. Okay. 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 So we prove one theorem. Okay. One another theorem. Let A and B are two numbers. Okay. Let and let F open interval a b to R be a continuous function. Okay. Then the following statements are equivalent. What is those statements? Number one, F is uniformly continuous on AB. Second one, limit x tends to a plus fx and limit x tends to b minus fx exists. Okay. Sorry, exists. Third one, f can be extended uniquely to a continuous function f naught on closed interval AB. Okay. So these three statements are equivalent. F is uniformly continuous on open interval AB. Second statement is left right hand limit at A exists and left hand limit on B exists. Okay. So second statement is right hand limit at A exists and left hand limit on B exists. Third one is F can be extended uniquely to a continuous function F naught on AB. Okay. So we are going to prove this result. This is very important result. Okay. So first is we are going to prove that 1 implies 2. 1 implies 2. Okay. Okay. So we are assuming that if possible, suppose that limit x tends to a plus fx does not exist. What does it mean? It means that it means that it means that it means that number one, it means either. So what does it mean? It means either limit x is plus infinity or minus infinity. Okay. Second option is limit x tends to a plus fx is plus infinity or minus infinity, and limit x tends to a plus something finite numbers L naught. Okay, two possibilities. It means you have not one limit. So whenever you approach a plus from right, you have two possibilities. Either it go to plus infinity, it will go to minus infinity. It will give you plus infinity or L naught, or it will give you minus infinity or L naught. Or another one, it oscillates between two finite numbers. L1 and L2, where L1 is not equal to L2. Okay. So what does it mean? Suppose we are taking case first. Suppose we are taking case first. So what does it mean? Limit. Suppose we are taking x tends to a plus. My function is approaching to infinity. Then by definition of uniformly continuity, so my interval is this a and b. Okay. Let epsilon greater than 0. Okay. Epsilon greater than 0. Then there exists a delta greater than 0 such that fx minus fy less than epsilon for all xy belongs to ab such that x minus y less than delta. Okay. Now choose y naught belongs to ab such that difference of with a naught of y is less than delta. We can choose it. Okay. Now if you take any x in between a y naught, then their difference will also x less x, the difference of x with y naught will also less than delta. But in that case, fx minus fy naught, where it will go? It will go to infinity when x tends to a plus. So what does it mean? What does it mean? It means, so which is a contradiction. Contradiction. Because fx minus fy naught should less than epsilon. This is contradiction to this statement. Yes. So this implies f is uniformly continuous on AB. Now, second case is settled. Similarly, you can show for limit x tends to a plus from right is infinity. The same technique can be done. Okay. So we are moving to case second. Case second. Case two. So limit one side limit is and limit x tends to a plus, that is L naught. So L naught, okay. Same technique can be taken. Again you take epsilon, okay. Then there exists delta greater than 0 such that fx minus fy less than epsilon for all xy belongs to I, such that x minus y less than delta. Same, same, same proof you repeated. Same proof you repeat as in case 1. Then it will be done. It will imply f is uniformly continuous on AB. Sorry. You move to first one. Sorry. Erase this. In case 1 you erase this. What we are going to prove? Here limit exists. So it means limit exists. Sorry. It means limit exists. Limit x tends to a plus exists. Okay. Similarly, here in case 2, we reach up to the proof that limit exists. Okay. Okay. So case third, we know that limit x tends to a plus fx is L1 and limit x tends to a plus fx is equal to L2 and L1 not equal to L2. So we will take epsilon is equal to L1 minus L2 by 2. Okay. That is greater than 0. Then there exists delta greater than 0 such that fx minus fy less than epsilon for all xy belongs to I, such that xn minus y less than delta. Okay. So but limit x tends to a plus is L1 and x tends to a plus is L2. So what? So it means there exists sequence xn and yn to I such that xn minus yn such that limit x tends to a plus fx such that limit x such that such that such that xn tends to a plus and yn tends to a plus. So it means their difference tends to 0. Okay. But in that case, fxn minus fyn both tends to L1. This tends to L1 minus L2. Okay. Okay. So from 2, we have L1 minus L2 is less than, what is the value of epsilon? L1 minus L2 by 2. And xn, we have xn and yn is less than epsilon because for all xn minus yn less than delta for sum, because this sequence xn minus 1 tending to 0, so it will, after certain stage, it will be less than delta. So which is a contradiction? Because this is a non-zero quantity, this is a contradiction, so it cannot be less than its half. Okay, this is a contradiction. This implies limit x tends to a plus fx exists. By similar technique, you can show that by similar techniques, you can show that limit x tends to b minus fx exists. So we are done. So 1 implies 2 is done. It is little bit lengthy, but you have to understand it, how the proof is working. Okay. So 1 implies 2 is clear. Now the statement 2 implies 3 we are going to prove. So 2 implies 3. Okay. Okay. So we know that limit x tends to a plus fx exists. Okay. And limit x tends to b minus fx exists. Both limit exist. Now I am going to define a function close interval a b to r such that gx is equal to limit x tends to a plus fx if my x is, I am taking a, okay, and it is fx if my x is coming from close open interval a b. Okay. And I am taking limit x tends to b minus fx if x is equal to b. So you see that function, this function has a quality. So g, the restriction of g on open interval AB. What does it mean? It is nothing but f function. Because if we take from open interval, x belongs to open interval, it is nothing but f. So it means gx on open interval A is nothing but equal to f function. Okay. So this implies G is extension of f on AB. So it is clear that this is extension. So now we are going to prove that this is continuous. So if G is continuous, what is the definition of continuity? So you see that so on x is equal to A is function G continuous. So we have to check if G at A is equal to limit x tends to A plus GA. But when we A plus means what? We are approaching to A from right. When we are approaching to A from right, it means we are in open interval. But in open interval AB, it is nothing but the function fx. Okay. But this is the value of, okay. So what we have to prove that? What is the limit? We have to prove that this limit will equal to GA. But in a, we are approaching to A from right side. So we are taking limit x tends to A plus GA. But on open interval, the function my G function is nothing but fx. So this limit is equal to this. But the meaning of we have defined function G, this is nothing but GA. So what does it mean? G is continuous on A. Now, similarly, at x is equal to B, what we have? At x is equal to B, limit x tends to B minus Gx. Sorry. It will be okay. X tends to B minus Gx is equal to, we are approaching to B from left. It means we are in open interval AB. So what does it mean? It means x tends to B negative fx. What does it mean? It means it is GB. So this implies G is continuous on G is continuous on B. Now, if we take any point in between, then my function gx naught is nothing but fx naught. But in open interval AB, my function f is already continuous. F is continuous on AB. So this implies G is also on AB. So it means my function G is continuous on closed interval AB. Okay. Now I got a continuous function whose restriction on open interval AB is f. What does it mean? G is continuous extension of f on closed interval AB. Okay. Okay. So we have proved 2 implies 3. What was 3? Yeah, we have proved 3. Okay. Now Now we are going to one thing is remaining. We have to show that this is unique extension. Suppose uniqueness of G. Suppose G naught is another continuous extension of G of F, continuous extension of F. Extension of F on AB. Then what does it mean? It means the extension of G naught at open interval AB will be F. Okay. But this is on open interval, it is equal to G also. So it means G naught is equal to G on AB. Okay. Now we have to prove on boundary. If it is equal, then G naught will be equal to G on closed interval AB. Okay. So let X tends to A plus. Okay. Then G naught A will be equal to limit, because G naught is continuous at A. Okay. But this is equal to G and this is equal to GA. Similarly, we can show that GB naught equal to GB. This implies G naught equal to G on closed interval A. So extension is unique. Okay. Okay. So extension is unique. So we have proved that extension is unique. Okay. Now 3 implies 1. So 3 implies 1 is obvious because G is continuous extension of F on closed interval AB. So it means this implies G AB to R is continuous and restriction of G on open AB is nothing but F. We know that every continuous function on a closed interval is uniformly continuous. This implies G is uniformly continuous on AB. But my function is defined, so this implies its restriction. So if some function is uniformly continuous on a bigger domain, it will be also uniformly continuous on a smaller domain. So this implies is also uniformly continuous on open AB, on open interval AB. But G is nothing but F on open interval AB. So this implies F is, because the function G is equal to F on open interval AB. So F is uniformly continuous on AB. Okay. So 3 implies 1 is true. So we have proved this theorem. We recall this theorem. Okay. So we have proved this theorem. What was that theorem? If a function f is uniformly contains on open interval AB, left hand and right hand limit exist, and f can be extended uniquely to a continuous function f naught on A not A or B, open interval, close interval AB. Okay. So we can take F naught is equal to G. In question I have defined F naught notation, but actually in proof I have taken G. So do not confuse. My G is actually F naught. Okay. So what is the why we are studying this theorem actually? Okay. It has use. So we are going to see this example. Suppose I am taking this example. If fx is equal to 1 by 1 upon x on open interval 0, 1, uniformly continuous. What is your answer? We know that fx is equal to 1 by x is continuous on open interval 0, 1. Okay. So by the theorem which we have proved just before, we know that if some function is defined on open interval a b and b are finite and function is continuous, then if it will be uniformly continuous if left hand limit and right hand limit. If right hand limit at 0 and left hand limit on 1 will exist, then it will be uniformly continuous. Otherwise not, because we have proved three statements which are equivalent. In that, one statement was that right hand limit at A exists and right hand limit or left hand limit at B exists. So similarly, now you see that if any limit does not exist, it clearly means that the function is not uniformly continuous. So what is the limit of x tends to 0 plus fx? It is nothing but infinity. So this implies limit x tends to 0 plus fx does not exist. Does not exist. What does it? It means fx is equal to 1 by x is not uniformly continuous on 0, 1 open interval. Okay. So by that from we have proved that a function is not uniformly continuous on the function fx is equal to 1 by x is not uniformly continuous on open interval 0, 1. Okay. So now we see second example. We see this example. Fx is equal to sine 1 upon x on open interval 0, 1. Is this function uniformly continuous on 0, 1 or no? So what will be your answer? So you see that limit x tends to 0 plus f sine 1 upon x. What is that? Because when we will go around 0, the limit will oscillate, oscillates, sorry, value of sine 1 upon x oscillates between -1 to 1. So this implies limit x tends to 0 plus sine 1 upon x does not exist. Therefore, thus Sine 1 upon x is not uniformly continuous on open interval 0. Okay. So, let's recall today's lecture. We have proved one theorem that if function f is continuous on an open interval, then it will be uniformly, if then the three statements are equivalent. F is uniformly continuous on open interval AB if right limit at A exists and left limit at B exists. And third statement is f can be extended uniquely to a continuous function on a closed interval. These three statements are equivalent. So by using these statements, we have shown, by using first two statements, we have shown that f(x) equal to 1 by x on open interval 0, 1, not uniformly continuous. Similarly, we have proved that sin x is 1 by x on open interval 0, 1, not uniformly continuous. Okay. And some examples can be done. Once we complete this topic uniform continuity, we will do several exercises. Okay. Then it will be more clear. So thank you very much for today's lecture. Kindly like, comment, share and subscribe my YouTube channel. Thank you very much. We will see you in next class. Thank you very much.